All right, so today we're going to talk about how the derivatives affect or can describe the shape of a function. And so we've talked a little bit about, in passing at least, hey, if you have a function y equals 2x, say e to the x, and where is this thing increasing? Where is it decreasing? How do you know that? Well, we've looked at graphs. We've seen that. Well, the derivative, of course, we talk about that. We can see what happens. We need to find y prime. Of course, that's the product rule. So it's 2 e to the x plus 2x times the derivative of e to the x, which, of course, is also e to the x. Now, this problem isn't too hard to do. Of course, we want to solve this, set it equal to 0. I mean, that's what we've been doing. Okay. And one way to do that would be to factor 2e to the x out. And it would leave you with 1 plus x. Yep. And so the idea here is that x equals -1, we have a 0 slope. Okay, well, that implies that we have a positive on one side of that and a negative on the other side. Well, how do I know? Well, e to the x is always positive, so this bit here is always positive. So it's going to hinge on this thing here. If your x is less than -1, so when x is less than -1, it's a negative slope. So it's decreasing, and when x is greater than -1, it's a positive slope. Well, let's see, if it was coming down and now it's going up, that means that -1 must be a minimum. Okay. And so that's kind of nice. That's interesting, I guess. So let's see if the graph agrees with us on that. Now, I want you always looking at the graph. If I don't see work on the derivatives, though, you get a 0 on the problem. Okay? I think a person should be able to be, first of all, smart enough to know that I wasn't born yesterday and I will catch you if you're cheating. But second of all, I would really hope that a person would be like, I don't know, I guess, honest enough with themselves. Not just with me, but honest with themselves to go, I don't understand this, and figure it out before you start. But here's the deal. When I look at that, I say to myself, well, that's interesting. Here, -1, what do you know? We've got ourselves a minimum. And the function is, in fact, increasing over here, and it's decreasing on this side. Well, that's kind of neato. Kind of swell. And so, great. It's a good check. But if it was at -2 or something, then I'd probably go back and go, maybe I messed up on my algebra somewhere. Well, the second derivative also tells us something. And so I am going to bring this piece here down and take the derivative of that. Well, the derivative of 2e to the x is 2e to the x. And this is the same as this, so that part will be the same as this. Make sense? And then if I set this baby equal to 0, and again take a 2e to the x out of everyone, I'm left with, this is 1 plus 1, so 2 plus x. Hey, that's cool. And you're like, what does the second derivative tell us? The second derivative tells us concavity. So this is concave up, and this is concave down. Whoop. And when f double prime is negative, she's concave down, and when f double prime is positive, it's concave up. Piece of cake. So it's equal to 0 at -2. That's cool. That probably means something. We're going to look at that in a few minutes. Again, this piece here is always positive, so when x is less than -2, we are concave down. And when x is greater than -2, we are concave up. And so when it's equal to 0, that is at -2, it is a point of inflection. That is where it changes from being concave one way to concave the other way. And you can see, friends, that right here at -2 is when it ceases being kind of opening down right in there. It's kind of opening downwards to opening upwards, and it changes right about there. Interesting. If one were to graph that function that we just did, Oops, I'm sorry, not that. Don't look at that. Look at that. OMG, gosh. It has, that is the second derivative, has a minimum, as a zero rather, where the original function has a what? Where the original function has a point of inflection. Okay? So that's kind of a big deal. Now you're like, Jay, you didn't graph the first derivative. You're right, I didn't. How awful of me. So let me graph the first derivative first, if you will. Here's the first derivative. Now, notice that the first derivative has a zero, where the original function has a minimum. That is a big deal. Further, let me put in the second derivative. Interesting. Now, if you don't mind, let me get rid of the red function a skosh. And let's just look at these two functions. Hey, weird. What do you notice about the green function, which was the first derivative? It has a minimum. Where? Where the second derivative, that is its first derivative, so this orange line is the first derivative of the green line. Are you with me on that? So if this green line were the original function, where it has a minimum or a maximum, that is where its first derivative would equal 0. So what I see here is I see on the original function, that is the red function, I see a point of inflection here at -2. I know it's a point of inflection for a couple of reasons, but mainly because its second derivative is equal to 0 there. And again, its second derivative, when it equals 0, that's where its first derivative has either a maximum or a minimum. So we're going to talk a little bit more of that as we go along. Okay? So, a couple things. I want you to keep that in mind as we go along. So, first derivative, wherever your first, not your first derivative, wherever your original function, so this is f of x, wherever it has max or mins, its first derivative will always have zeros. That is a big deal. And if you take your pen, like I'm going to do here momentarily, I'm going to make marks here and probably about here, because what does that look like? That is where we have minimums or maximums. And what is the slope at a minimum or maximum? Well, the slope is 0, of course. Now, over here, this function is going uphill, correct? That is, it has positive slopes. Try to redraw that. It's positive slopes. Are you with me? Positive slopes. Now, down and through here, what are these guys? Well, they're negative slopes. Where is this the steepest? I feel like the steepest is right around in here somewhere. Do you buy that? That's about where it has the steepest negative slope. So, in other words, when you're drawing this, it's going down, 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 and that is where it has the steepest negative slope, and then it's still negative slopes, but they're getting less and less and less until you get to here, which is interesting. Now, as you go along, you can see that right around in here somewhere, where it has the maximum upward slope is somewhere in this. Well, it's more like maybe right in there, actually, right? And then it starts to peter off that way, so maybe right about in here. And then it kind of notice that there's still positive slopes. Still positive slopes until I get up to that top of the deal. So this guy is f prime of x. Well, you're like, well, can you draw the second derivative? You know I can. Hey, look at this. This is a minimum value, yes? Well, that means the slope of at that point would be 0. And this looks like a maximum, so its slope would also be 0. Interesting. Notice that these guys here are all negative slopes, which means I'm going to draw them down here like so. But you're like, wait a minute. This blue line is f double prime. Notice how it is negative down here. Do you see that? Look at the black line. It is concave down. That's right. Now, here it changes from being concave down to being concave up. And so between here and here, what do you got? We have that this function, this black function, is concave up. And from here to here, the red line has a positive slope. And then notice it's concave down again. Something along those lines. Okay? And so you can sketch them till you're blue in the face. The way to always start is to start off with the maximum minimums, like as I said, right here. Go up there and make a mark. At the maximum minimums, you will always have zeros. Start off from there every time. Let's do another one. So y equals 3x 1 minus the square root of x. Awesome. And yes, that can be written in several different ways. I could do it with a product rule. I could do it and just distribute it out. I think I'm going to go ahead and distribute it out because I think I'm a little lazy. And this is 3x to the 3 halves, I think. So if I want to take the derivative of that, it's going to be 3 minus 9 halves x to the 1 half. Right? And you're like, well, where does this baby equal 0? I don't know. So I'm going to add this mess to the other side. Multiply it over, I'm going to get 6/9. And then I'm going to square both sides. And this, by the way, is 2/3. Square both sides, I'm going to get 4/9. Right? Right. If I square both sides, I get 4/9. Right. This right here should be where I have a maximum or a minimum. Okay? Now you're like, which is it, Jay? Well, I don't know. I don't know. So if you put in, like, say, 10, what's the square root of 10? Well, it's like 3-ish. And 3 times 4.5 is 12 something. 13.5 is what it would be. And what is 3 minus 13.5? Well, it's negative. That's right. And so when x is greater than 4/9, it is going to be increasing. And when x is less than 4/9, now be careful a little bit. Be a little bit careful here. It is decreasing. However, it's a square root function, so it only goes as far as 0. Okay, so let's go look at this thing. Remember, this is our original function. So it's, what did I say, 3x, no, I said 3x, there you go, minus 3x to the 3 halves power. And a little zoom action there. Oh, click it, 0.44, which, by the way, is, that's right, 4/9. Notice how it was going uphill until you got there, and now it's coming downhill. Awesome. Now, where is this thing change concavity? It doesn't change concavity because it's always concave down, isn't it? Now, let's take the second derivative. So I'm just going to rewrite that. So y prime is 3 minus 9, what did I say, 9 halves, x to the half. Let's take the derivative, shall we? So that's y double prime. Derivative of 3 is 0, of course. This is going to be minus 9/4 x to the minus a half, or minus 9 over 4 square roots of x. When does this equal 0? It never equals 0. Furthermore, no matter what value of x you put in there, as long as that is greater than or equal to 0, because that is the domain of the function. By the way, the domain of this derivative, the domain of the derivative is just greater than 0. Okay? But notice the original function, the domain was x is bigger than or equal to 0. Okay? And you might remember we talked about on the day 1 of derivatives. Right? The derivative, remember, is a limit. So I can approach it from both sides. Well, I can do that here. I can do it everywhere except at 0. Because it didn't exist, and then all of a sudden, boom, it exists. How fast did it have to change to get there? Infinitely fast. So, yeah. But here's the deal. As long as you pick an x that is bigger than 0, the square root will always be positive. Times 4 is always positive. And negative 9 divided by a positive number will always be negative. So f double prime, or y, I should say y prime, the way I wrote it, y prime is always less than 0, which means it's always concave down. That means there is no point of inflection. Okay, let's do another one. Sure, let's do that. So f of x is 3x squared minus 4 ln of x plus 6 over x. Hey, that's cool. Furthermore, we know that this guy from here, x has to be bigger than 0. I'm sorry, I lied. I was pointing at the wrong one. X is not 0 on this one, yes? Here we know that x is bigger than 0, yes? Which means, which is the more restrictive? This guy is the more restrictive function. So when we do this in a few minutes and we go look at the graph, we're going to see that that is our domain. And we're going to see that that may or may not be true for the domain of our derivative. It may be a little different. So it's 6x minus 4 over x. Remember, this thing here is 6x to the minus 1, right? So it's going to be minus 6x to the minus 2, or if you prefer, 6 over x squared. Okay? Now again, this is less restrictive because here it's just x does not equal 0. But remember, our actual function is strictly positive. Okay? So when I go and look at this, and you're like, Jay, why do you make a big deal about that? Because in Calc 2, 3x squared, in Calc 2, we're going to see that when you take the integral, which is something you'll learn about later, for instance, the integral of 1 over x is the ln of the absolute value of x. And you're like, why, why, Jay? Well, I'll tell you. The reason for that is because 1 over x goes all over to, everywhere except not 0. But the ln of x, the derivative, is 1 over x. But only the part that is greater than 0, because the function ln of x does only exist for positive values. Okay? Now, you'll notice I didn't get around to solving this yet, did I? I need to set this baby equal to 0 and solve. Watch me multiply through everybody by x squared. Now, I can't solve that. I'm not smart enough. I used to be, but I'm not anymore. So what I'm going to do is I'm going to graph that 6x cubed, and of course, you're like, Jay, can we do that? Well, of course you can do that. That's, yeah, duh. Minus 4x minus 6. And I'm looking for the 0 of this function, and it's right there. It's 1.219. Notice that that is where our minimum occurs as well, is it not? What? Bam. And so we have this happens at 1.219. What if this thing had a 0 at negative 3? Here's my question to you. What about it? Because this function right here exists on the negative side too. But we don't care about what's going on there. We only care when x is positive, and this is the only solution. So when x is bigger than that, I don't think it takes a rocket surgeon to see if you plugged 1,000,000 into there, 1,000,000 cubed is positive, minus a little bit, it's still positive. So the function would be increasing. And when x is less than 1.219, it is decreasing. Now be careful. Again, from there only goes as far as 0. Okay? And so we're going to see that. Now, the question is, I shouldn't say the question is. The question, of course, being, that is a decreasing function, right? Now, is that what we saw over here? Yeah. This black line is coming down, 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 down until it gets to here, and then it takes off and goes back up. That's true. Okay? Now, concavity, hey, can I take, now notice I was solving this. I cannot use this to take the second derivative. I need to take the second derivative of this guy. So it's going to be 6. And this is going to be plus 4 over x squared, because this is negative 4x to the minus 1. And then this is negative 6x to the minus 2. So it's going to be plus 12 over x cubed equals 0. And you're like, okay, well, same thing as last time, times everybody by x cubed, except times everybody by x cubed this time. And set this baby equal to 0. Now, you may have been paying attention and see that black line right there? It's always opening up, isn't it? So where is it concave up? It looks like everywhere to me anyways. That's what it looks like. I don't know that I'm right, but it's what it looks like. So 6x cubed plus 4x plus 12. Yeah, baby. Now, some people would go, right here, there's a negative right here. Yo, we're only interested when x is positive. So does the second derivative equal 0 on the positive side? And the answer is it sure does not. What does that say about our function? It says our function, it says that this thing never equals 0. Well, if you think about this, if you're putting only positive values in, these guys are all positive, which means that f double prime is always positive, which means it's always concave up. And that's what you're going to be doing. This is in section 4.3. So just be aware of that. You'll be asked a ton of questions about these things. Take the first derivative, set it equal to 0. Find where it changes from being positive to negative. Just be aware of that. I will do one more, I think. This one's kind of fun. So if you do f of x is equal to x cubed, of course, any idiot knows how to do this problem. Of course, well, let's do plus 1 because that'll make it cooler. Yeah, so f prime of x, 3x squared. Hey, where does this guy equal 0? Wait, equals 0 at 0, Jay. Hey, you're right. You're right. What if I put in negatives? Well, negatives squared are positive, and positive squareds are positive. Wait a minute. So the function was increasing. That is, it has positive slopes when x is less than 0. It also has positive slopes, and it's increasing, that is, when x is bigger than 0. What? Well, here's what x cubed plus 1 does. It does that. It has a plateau, if you will, for just a microsecond or whatever right there, at 0. It was increasing, it stopped, and then took off and increased again. Interesting. Hey, now, let's take the second derivative. Second, x6x equals 0. That means x is equal to 0. Well, interesting. If you said this, so it changes. Well, what if you put in a negative? Well, then it would be negative, so f double prime is less than 0 when x is less than 0, and it is positive when x is greater than 0. So it's concave down, concave up, which means that this guy right here is a point of inflection. Nice. And of course, you come back over here, you can actually see that x cubed plus 1. Bam! Boom. And I think you can all see that. Increasing, stopped, increasing, concave down, concave up. Boom. What? Done.